Well, let's take this one step further and consider the forces in a finite but uniform distribution of masses. So each one of these masses has the same mass, m. They're all separated by exactly the same distance, d. We find that the force on the one in the middle is exactly 0 because all the forces cancel. We can take the forces by pairs. We can take this one, and we know that those forces cancel from the last slide. And then we say, okay, well, we have to consider the force on this mass from this one, and that's exactly balanced by the force from this one, and so on. So the force on the middle one is still 0. But now let's consider another mass. Let's take this one here. Well, the force on it is, let's take it by pairs. Let's consider these two masses. They're equal and equidistant, so those forces cancel. Then this one and this one cancel. When you get here, that cancels with this, so the net force is still 0. But now there's one more particle, one more point mass over here, and its force is not balanced out by a mass over here. And so this particle feels a net force in that direction. And this force actually increases as we consider these particles, and that's easy to see. If we consider this one, those forces balance, those forces balance, but now this particle feels an unbalanced force from this, and this particle. So it feels a negative force, and it's larger in magnitude. And so this is what the forces would look like in this finite but uniform distribution of matter. Now let's consider an infinite uniform distribution. Something very interesting happens. All the forces become 0 on all the particles. Now, how can that be? How can we see that this is true? And by the way, this was first explained by Isaac Newton in his Principia. It's easy to see how this must be the case. Imagine this line of masses extending to plus and minus infinity. Such a line has no center. Another way of thinking about it is any place on that line is just like any other place because the particles extend to infinity in both directions. So if every particle is the same, and if you pick any particle and realize that there is an equal and opposite force coming from both directions because they extend to infinity, those forces cancel and you have a net force of 0. It can't be anything else. And so this is an interesting case and a very relevant case to cosmology because we live in an infinite universe. It's a three-dimensional universe if you like to think Cartesian. It's a four-dimensional universe if you like to think Einsteinian. But this simple model applies in any direction you like. I could have shown a two-dimensional or a three-dimensional array of point masses, and as long as they were equidistant and infinite, you would conclude that the net force on any particle is 0. However, if we take just one particle and we displace it slightly, as I've done here, that's no longer the case. And that's easy to see. The particle was here. We move it a little bit to the right. Now it's a little closer to this particle than that particle. And because the force goes as 1 over the distance squared, the force from this particle is larger than the force from this particle. And so there is a force to the right, as indicated by this arrow. And because forces are equal and opposite, from Newton's third law, this particle feels a force in that direction. Now, This particle had no net force on it because it was exactly balanced by pairs. If we move this particle to the right, it's now a little further away than it was, and so this particle now exerts a greater force on it. And so there's a net force on this particle pushing to the left. And in fact, the forces on these particles are also not zero, but they decay away, and I just haven't shown that here. So you have forces pushing to the right and the left, and all you've done is you've displaced one mass from its perfect equidistant separation. One way of thinking about this is, if we consider this a region of space, we've made the density of particles in this part of space a little higher, which is why I have the plus sign here. It's a slightly denser region of particles here, and we have forces that want to bring those particles together. Over here, we have a lower density distribution of particles, which is a minus relative to the mean, and that creates a force that pushes them apart.